Yeah,
Okay,
go ahead.
okay. Uh, Welcome again. Okay, in the second part, I will try to speak a little bit about some results we obtained with Fernando Cipriano about the well-posedness in the presence of multiplicative noise and some story related to the invariant measure in this setting. So, okay. So generally, let me try by some good picture. I just like to give you good motivation about this Newtonian fluid. So there is a huge literature about Newtonian fluid, basically that's coming from the Navier-Stokes equation and around it. And the typical example is you have water and so on and so forth. But you can just like think a little bit about the two pictures that I'm showing here, a magma volcano or a butter that when you heat it, you can see a different future. So this picture show you that you have something in the nature that may share something similar to the water, but they behave totally in different way. So we should take in consideration that. And as a consequence, let me write some physical fact that generally, if you talk about the viscosity, and I will be precise, but what I mean by viscosity is what a measure of fluid resistance to flow. So if you have a fluid that in flow and you see the resistance, then I will call the viscosity. What is typical about non-Newtonian fluid that this viscosity change under the stress. The stress is some forces. And you know that when you have when you are a certain flow, you have some internal force, some external force. So you have a lot of forces. And this kind of Newtonian fluids may behave like a viscous or elastic object are viscoelastic fluids. So they have many properties like shear thinning and shear thickening. But for example, if you take the water, you don't have such property. So generally, to simplify the things, when you think about the viscosity, you should think that your viscosity is a function of the pressure and some external force, and also maybe the temperature, and also some internal forces if you are writing the equation of velocity. So it would basically mean the gradient of the velocity. And typically for the Newtonian fluids, the relation between the shear stress and the shear thinning is linear. And then the viscosity is not changing over the, the stress that you have under your flow. Then typically you have the Navier-Stokes equations. Where you can find such non-Newtonian fluids, you can find many of them. If you think about the shampoo and some paint and some geological flow, they are all non-Newtonian fluids. They are geological fluids. And then for classification of fluids, you have the Newtonian fluid, which typically can described by Navier-Stokes. Then the second grade fluids that I'm not going to talk about. Then I'm going to talk about the third grade fluid, which is a class more general. Second grade fluid is the special case of the third grade fluids, but they have many interesting features. So this is what I am going to talk is the third grade fluids. I'm just writing some reference for physical motivation why we should consider third grade fluids. It's studied from physics point of view, and these fluids exist really. They are not. We don't just keep complicating the thing. It's something exists. In the other part, why I'm considering the noise or the stochastics. Having in mind some ideas, like if you think about Navier-Stokes equation and you take the viscosity term, if you are probabilistic somehow, you think this term as diffusions, and diffusion for you is somehow Brownian motions. So this is come from somehow the small scale, and small scale, when you take a fluid at some scale, if you see the trajectories are Brownian motion. So thinking about smaller scale interaction, somehow you should have in mind some Brownian motion in your systems. Another thing is there is many debate about what kind of boundary condition that you should put in your system. Either you put Dirichlet boundary condition, Newman boundary condition, or you mix them, or whatever. So there is many debates and people don't find a point. So I hope that when I add some randomness, I can somehow compensate some problem that may come from boundaries. Of course, some numerical approximation argument. And of course, there are some arguments that come from modelization point of view. I don't want to go deeply in details, but just many motivations that push you to incorporate randomness in your system. So let me tell you first how I can derive my equation. So if you consider the symmetric part of the gradient, which I denoted by I1, and then you write AN, which is river electron kinematic tensor, which is some tensor that depends on T. You write the constitutive law of a fluid of grade N. The grade N, it will be the Newtonian, grade 2, grade 3. So for my case, I will talk about N equal 3. It will be written in the following form. The T is minus U, which is basically the term that gives you the pressure in your equations. And some function depends on this family of IE that I wrote down, where F is some isotropic function, in the sense that when you see your fluid or viscoelastic fluid is, you have certain symmetry in all the direction. You don't distinguish between one direction and another. And if F is some polynomial of degree N, that we are talking about the fluid of grade N. So I insist again, my N equal 3. So typically, when you write the previous relation, you will arrive to this. So I write it in purpose in this way. So you will see that the first two parts in a black color that correspond on the derivation of Navier-Stokes equations. If you add the blue term, then we are talking about the second grade fluid equations. And if you add the red term, then we are talking about third grade fluid equations. There are some physicists and people, they consider the thermodynamic properties and stability, and for example, that the free energy at the rest, it's minimum. Then you have some relation between the parameters. Like you have the parameter me, but you have the parameter alpha 1, alpha 2, beta 1, and so on and so forth. So for the second grade fluid, you have this Closium-Duhamel inequality, which is give you in which setting you should consider second grade fluids, and therefore you should use it when you write your equations. And for third grade fluid, you have similar equality, which is called Fos-Dick-Rajobal, and it tells you that this parameter should respect some relation to be that your equation has a physical sense somehow.
Yassine, just let me interrupt you before it gets more involved. So when we look at grade 2 or grade 3, does it smooth better, or it's just more complicated?
They have some common things, but the thing I would say, it's there is common things. There is some differences. You will see when I wrote the equation, you will see clearly what is maybe good, but in 1 second it became bad, and vice versa. So,
okay, but just in terms of the smoothing effect, is it better, or is it the same in terms of the Laplacian, for instance? It smooths by two derivatives, and when you add,
I see. I mean, I see your point. What I'm saying is, you shouldn't think about these things only that, because when you write your equation, you don't have only Laplacian. You have some nonlinear term, and you have some more nonlinearity in the convective transport term. So they make your problem is more complicated in some sense as well.
Okay, so you gain something, but on the other hand,
there is a competition between many terms.
Okay.
When I write the equation, you will see. So
okay, thanks.
Okay, so I'm just repeating here that I am considering physical domain that may be in 2D and 3D and simply connected, which I say it's important to be simply connected domains. So you consider the probabilistic stochastic basis stuff. And therefore, my noise that it will satisfy certain assumptions. So you consider family of Brownian motion, but this is the result hold for general Wiener process. But when I am talking, just keep thinking about Brownian motion. I'm just here writing the general setting, but you can think about just Brownian motion, just like to give sense to the Wiener stochastic integral. And as I told you before, that when you take this stochastic integral object, it have the property of martingale when you see it as an object in L2. So this basically, when you have this assumption, you will have such information. If you have your solution, have some regularity. And of course, if your solution should also have this measurability with respect to omega and t, and keep in mind this adaptivity stories. Let's go to our equation. So if you write the momentum equations, so the total derivative.
Yes, Yassine, can you just go back? Just when you talk about the square integrability of your noise, sigma, is there a supremum norm on the second variable or something like that? When you say the sum of
this one, sum a square.
What is A? What is A? I thought it's sigma before.
The sigma is your coefficient, right?
Yeah. Okay. Yeah. Okay, I see. As gradient of sigma is less than I
bounded by
and
something
I.
that the summation is
Okay.
finite to give sense to the finite and infinite sum.
Yeah. I didn't see just the
I mean,
inequality.
in fact, we are assuming more than expecting because I'm expecting, I am asking that the gradient to be bounded. Generally, we assume that the sigma k only bounded. But here, because I'm looking for more regularity in space, because I wanted to construct more regular solution to my problem.
Yes. Okay.
But it's in the same spirit.
Okay. See, thank you.
Okay. So if you write the momentum equation, so you have the total derivative equal the divergence of this constitutive law. So you have this nice system. What do you have? You have the following. Instead of having time derivative of u, you will have time derivative of u minus some coefficient Laplacian u. And this tells you somehow you have more regularization at first moment. Then you have the three terms that you know from Navier-Stokes equations. If you take only the three terms from Navier-Stokes equation and you just think about the term that is written in blue color, the term beta, then coming back to the question of Harun, this term of beta has more regularization effect than the Laplacian, because the Laplacian will give you the gradient is square integrable, but this will give you because A is the symmetric gradient of the velocity. So if you use corner inequality, you will have it's for integrable. It's like more you gain more integrability of the gradient. But you will see immediately that you have divergence a square, which give you some more convective term, and you will have three derivative in the no convective term. So you have y grad Laplacian u, so you have three derivative coming from this term in the transport term, and this makes your life horrible. So it's a mixture of parabolic, hyperbolic, and if you compare it with Navier-Stokes, you see that if the viscosity is very high, your system is more parabolic, so it's more regularized. If the viscosity is very small, so it's more hyperbolic, and then you can think about your equation. But here the future is somehow similar, but it's also complicated from a PDE's point of view analysis because you have more derivative and more nonlinearities to manage. I am adding some external force, and in the presence of some stochastic part. Of course, I'm adding the free divergence property. What I am saying in this first part, I am talking about Navier-Stokes boundary condition. So I'm saying that the velocity, the normal component velocity is 0 in the boundary. And the second part of Navier-Stokes boundary condition that the friction, when you see the gradient symmetric at the boundary in the tangential component, it will be 0, and it will tell you that your fluid travel near to the boundary with no friction. Okay, so this is the equation that I wanted to tell you a little bit about in the first part. It's complicated. Okay, let me try to some functional spaces. So when I say H, I will consider L2, but I will put inside the free divergence property and that the normal component equals 0 on the boundary. If I increase, you consider the space of H1 with the same properties, then I will denote it by V. So if you consider more regularity in H2, then I can give sense to this on the boundary in some Lebesgue spaces, and this I will call W. And I can more regular spaces that I will denote W tilde. Note that if my domain is simply connected, and the alpha 1, and remember this alpha 1 is the term that appear in the V term, you have y minus alpha 1 Laplacian u is strictly positive, then you can prove that the following norm or the following scalar product in the space HV, W, and W tilde are equivalent to the usual scalar product in H1, H2, and H3. Okay, so this is basically for the simply connected and alpha 1 strictly positive. If your domain is not simply connected, this is not correct. If alpha 1 equals 0, this is a totally different story. I will tell you something about it at the end of my talk. So what I mean by local solution in my stochastic setting. Generally, when you do deterministic, your local solution, you are looking for a positive time that depends on the data that where your solution is living to it. But in the stochastic framework, your local time will be some time depends on omega. For almost every omega, you have different time. But what you are looking for something strictly positive, if you see it as a function of omega, and the dependence of these two on omega should respect the measurability with respect to ft. This is a first part of the local solutions. The second part is looking for some regularity of your solutions. You have some integrability with respect to time, with respect to omega, some continuity in time, and also some regularity with respect to the space t and so on and so forth. Something I wanted to say is the following. When you do deterministic theory, you see the space L infinity 0 to W, you have some solution is there. When you do the stochastic, since your solution will be understood in some duality sense, and the space L infinity is not separable, you lose Radon-Nikodym theorem. And therefore, to apply Banach-Agolod theorem, you have problem in some dualities. You know how to fix that the DL of, if you put L1 and you put the DL of W tilde prime, you will have, and you put LP prime, the DL of this space will be this space I wrote at the end, but the measurability with respect to omega when you see it, you see the measurability as a map from omega in the space L infinity 0 to W tilde, where you put the weak star topology in this space and not the topology of norm. Your equation will be understood in the following sense. So you take some test function, as you know, and you integrate your time. You consider your equation integrated in time, and this is related to this non-derivation of the Brownian motion. So this is if you wanted to compare it to the deterministic theory. So in comparison with deterministic, you should have some stopping time depends on omega and respect certain measurability. Your solution should respect more a constraint on the measurability to give sense to the green stochastic integral. This is somehow a formal differences in the clear way when you see the definitions. And of course, if you are the deterministic, all these things argument are of course correct. If you have only one time, it will be automatically measurable. How I understand uniqueness? I understand uniqueness in the following sense, because I'm looking for local solutions. So if you give me a solution and the local time of existence of two solutions, then I say I have pathwise uniqueness when I calculate the probability where the solutions are equal under the minimum of 2 times that probability equal 1. Then I'm talking about pathwise uniqueness. And in the same spirit, I would talk about maximal local solution. So I can construct local solution, and then I have the right to ask if it is maximal, or can I extend it to be maximal under certain blow-up. So what I mean by maximal in this setting, because I have the extra problem of measurability, I need to be careful when I construct maximal solutions. So it would be maximal if I can find a sequence of stopping time that for every element of this sequence of stopping time, I have local solutions, and this sequence of stopping time converge monotonely to this maximal time, where my solution, if you want, you have some blow-up criteria. What about the data? I will consider my initial condition and my force, respect the measurability with respect to the filtration. Because if you give me some force, it doesn't respect the measurability with respect to my Brownian motion or my fixed filtration, you can't expect my solution to to respect it. And of course, they satisfy certain regularity with respect to t and x and omega. I am starting with some data living in H3 with free divergence, satisfying Navier-Stokes boundary conditions, and I wanted to construct H3 solution to my system. So how I do that?
Sorry, so can you just go back one? Yes. So the second item, the second bullet point, do you really want the sup of the solution to be larger than m?
No, you don't want, and you will have it somehow, because when I define the stopping time will be something depends on this norm WT in the space W24.
Yes, but this condition means that as m becomes large, then the sup will blow up, right?
Yeah, this is my point. I mean, the maximal solution in the sense that if you wanted to see the solution up to this t, which is written in MATPF,
yes,
your solution will explode. This norm will require infinity formally. So in some sense, for every tm, it's a stopping time. This norm somehow will just arrive to m. Then you consider sequences that when m gets to infinity, this blow up, and then you are talking about your maximal solutions.
Okay. It looks unintuitive for me, but it's okay. Yes, I will.
Okay. I mean, maybe I will more when I will go to the proofs. When I say something, maybe we see it better, because maybe
thanks.
At this level.
Yeah, thank you.
Yes, I mean, yeah, you just forget about it, but I think it comes from when you write the proofs, you will see that how to define your stopping time. I have that, but the definition of maximal is basically only the first point, basically. Okay, so I'm saying more here that you have some blow up. So, okay, so what's the theorem that I wanted to prove? That in the sense they are precise previously, you can prove the existence and uniqueness of a maximal solution to my initial problem. Coming back to your comments, so the time interval 0t is the maximal interval of the trajectory of our living, and having this stopping time argument, you can see that this norm H3 will explode when you reach the maximal time, because I am interested to construct H3 solution. Why am I interested to understand or to construct H3 solutions? Because I wanted to understand my equation in pointwise sense and not in distributional sense. You see, from all these different nonlinearities, if you have H3 regularity, you can prove here that your solution is understood in some Lebesgue spaces. And in other sense, when I consider a solution in the probabilistic point of view, I'm considering a strong sense in probabilistic sense that I don't change my probability space and my Brownian motions, which is the something related to when you think, for example, about the notion of martingale solution, which tell you that all this quantity, omega, the sigma algebra, are a part of the solution. So I'm also interested to construct solution on a given probability space and a given Brownian motion. All what I'm going to talk is from the paper that appear down here in this slide, and it's just published in the last month. Okay, so what is the technique of the proof? There is many futures, but maybe I will say something about some future and I will skip the others. The strategy is the following. The first step is you use a Galerkin basis, basically finite dimensional approximations. But keep in mind that you have a lot of nonlinearity. And having free divergence property, Navier-Stokes boundary condition, the basis that you choose to use Galerkin method should be compatible with that. So what we do, we consider when you see the compact ambident of the space W tilde in the space V, you have the compact ambident thanks to Rilish-Kontrashov theorem. And you have the information about the free divergence and the boundary condition there. Then when you see this operator of the compact ambident, you can consider the corresponding eigenvector in these two Hilbert spaces. And you consider this eigenvector as a basis that you use in Galerkin approximation. This is the first step. Since I have a nonlinearity, how I can solve a nonlinearity or how deal with the linearity? I will somehow cut my nonlinearity with certain appropriate cutoff function. And this nonlinearity or the cutoff function that at the end, the way I choose it in the beginning, it's the way how I will choose my stopping time depends onto it. When I include some cutoff function, I have more Lipschitz stochastic differential equations. Then you can use some fixed point argument to construct solution for this modified problem in the presence of cutoff in finite dimensional setting. Once you have this, you wanted to have some information about your approximate solutions. I don't maybe probably go deeply into details. I will say something in the next slides, but it's more how to derive some estimate. And basically, you should apply Ito formula, define some appropriate stopping time to deal with the stochastic integral, and you call the Martingale inequalities, typically Percolder-Davis-Gandy inequality, do some estimate, and at the end, you will have some information. By using these informations, you consider the corresponding law of some quantities, and you prove the tightness, and then you call the Prokhorov theorem that I recorded in the beginning about the tightness and the convergence of some subsequences in weak sense in the space of measures. And then I will call Prokhorov theorem to construct a Martingale solution in the sense that I will construct a new probability space, a new Brownian motion, and where my solution lives there. So this is the strategy. How we do that? This is just the definition of Martingale solutions that I said. I will add that this quantities omega, f, and this filtration and the probability measure and the Wiener process are part of the solution. And this will become by using score code presentation theorem. And I keep the information about the integrability and the formulations. Another thing that when you start with some initial data and force that depends on omega, what's still invariant when you change the probability space is the law. So I'm not talking anymore about y0 and u, but I am talking more about something u tilt and u bar, but they have something common, which is the law. They have the same law. When you do some estimates, you can prove that your solution satisfies some a priori estimate. And basically, it has some H3 regularity in space, infinity in time. And you can use this information to deduce that when you see your equation, you see it in abstract sense, you can split your VYN as deterministic part and stochastic part. For the deterministic part, use the information of the regularity of the solution, and you can prove the first point by doing some computation. The other part is the stochastic part, having some information about my solutions. I can use some fractional regularity in time of a Martingale, basically due to paper of Flanduli and Gaterek. And I will catch an information about fractional Sobolev regularity in time of the solution. And therefore, I will deduce some Holder regularity in time by using some embeddings. As conclusion, what I have, using all my information, I will prove that my solution UN is bounded in this space written down. It's L1 in omega with this space, Holder continuous function with value in V, L2 in omega, L infinity in time with value in this WT, which is basically H3 with the free divergence and the boundary condition. What this information will help me to do, if you forget about omega and you see C eta 0TV intersected L infinity 0T W tilde, and you go to the paper of Simon, you have the compact embedding that I wrote in the beginning of this slide. And you see that I have a compact embedding in the space of continuous function with value in W24. This is why I choose W24 in my formulation. Of course, it's not sharp. You can change, depends on space dimension, but you can do it in 2D, you can do it in W2 key for key finite. And in 3D, you can do it for W2 key less than 6, strictly less than 6. So just my choice that I put for here. So then we define the following path spaces. So I will put a vector where I put my Wiener process as a component, my solution of my problem, my forces because I'm going to use the Prokhorov theorem, and my initial condition. This space is a Polish space, and I consider the law of all my random variable in this product space. Thanks to the boundedness information I have, I can consider the ball in this space Z in the beginning of my slide, which compactly embedded in this space. So this set is relatively compact in the space of continuous function W24. And this tells me that I have tightness of the law of my solution Yn. Since my Wiener process is a single radon measure in this space of the paths, it's also tight. Since I have strong convergence of the projection of my force and my initial data, then you can use Prokhorov theorem to prove that you can have a compact set that you have the tightness for these two components. Then you use Tikhonov theorem of the product of compact set in product topological space, that the joint law of all this variable is tight in the product space, which is I'm writing at the end. You apply Prokhorov theorem, then you can extract subsequences that converge weakly in the sense of measure, which interpret as a convergence law to some probability measure I will denote it by U. Then I will score code presentation theorem. Since I have convergence for subsequences in law, which means it's tight in somehow, I can find the new probability space and the new random variables living in this product of these vector spaces, where I have probably almost surely convergence of these new variables, and they have the same law of the previous previous random variables. And then I have the first point, that equality of law allow me to transport my approximation from the previous probability space to the new probability space. The third point will allow me to establish some strong convergence by studying the integrability of new random variables. So since I have a new probability space, sigma algebra and probability measure, first step to fulfill my definition, I need to construct an appropriate filtration to keep my stochastic approximation, approximation problem is defined with respect to the new sigma filtration. And also I will define similarly filtration to my problem at the limit. Generally, typically, it will be some sigma algebra generated by my solutions, and it will be right continuous. This is not difficult stuff. Then I will have my new problem in my new probability space by using my new random variables that they have the same law, but they have the advantage that they have almost surely convergence in the corresponding Polish spaces. Thanks to the equality of law, I can maintain my a priori estimate for the new random variables. You can use Vitali theorems, probably almost convergence with some uniform integrability. You can deduce some strong convergence. Then you have a list of a convergence which allow you to pass in the limit, in the nonlinear term. And you construct solutions in new probability space with a cutoff. This is what is the price that you pay. So when you pass to the limit in your approximation, you pay the price by using score code theorem, constructing your solution in new probability space. So you pay this price. And second, because your problem is catastrophically non-linear, you introduce some cutoff and you are modifying the problem. So you have some modified problems. And of course, by using cutoff, you are adding more nonlinearity. And even with such regularity, you have problem of uniqueness of such solutions. But since I said in the beginning that I wanted to construct solution in my initial probability space, what I will do is the following. I will modify my problem. I will consider some problem based on the problem that I solved, where I put some stopping time, where my solution is global, but I will have some stopping time inside my problems. And I can prove uniqueness of this modified problem. Then there is something in probability theory that told you that if you have martingale solution, this means that solution that I just constructed, and you can prove uniqueness of these solutions, then in fact, this solution is constructed in your given probability space. And in somehow, it's tell you that the randomness of your system come only from the data, means the system doesn't inject randomness anymore in your system. Okay, then to construct local solutions, I will define this sequence of stopping time, and I will use some monotone argument to consider maximal solution. This is the general overview how to do it. For more details, the details are the following. When I define the cutoff function, I will put this y infinity w2 for non inside my cutoff. And as I told you, it's just a choice. So you can, what you can do, but you can do also for w2 key less than 6, and is basically related to the embedding of h3 in wt6 in 3D. And you can do w2 key less strictly than infinity, and this is related to the compact embedding of h3 in w2 key for every key finite in 2D. And you know that my compactness argument is somehow crucial. So I define this following stopping time argument, stopping time. And since I have boundedness in h3, this is strictly positive. If I start, I am sure that I have strictly positive time while my solution lives. Then, if you define a solution that lives up to this stopping time, then this solution, as I said, is global in time. This is what I mean that I include stopping time, and I get my cutoff. I get far from my cutoff because I am putting this inside my cutoff. Then I prove the following stability result, which told me, give me the uniqueness, pathwise uniqueness that I precise in the beginning. Again, the same thing that I'm saying here, just resuming what I was saying, that you have sequence that depends on M, because every time you fix M, you have stopping time and you have local solution. This is a local solution, but it is not maximal. Now I'm here in this slide, I'm just saying there is different version of that, what they call the Yamada-Watanabe theorem, that there is basically I can use this version from this paper. If you have a compatible solution, and it basically tell you the following. I tell you that the data characterize completely the randomness in the problem. I don't have new randomness coming from my dynamic. Then I can couple these two arguments to construct unique solutions up to certain stopping time. So I have some solution in my given probability space up to certain stopping time. Then how I can construct maxima? I will use the argument of uniqueness and monotonicity. So this family of stopping time that I defined here, it's clear that it is monotone. To M is monotone. When M is increasing, to M is increasing. I will consider the limit, which is the C primum, and I will say that my solution up to this time t is given by, for every M, the solution until the time to M. And then I extend until I reach the maximal solution. And I mean by maximal solution, where this norm blow up, which leads that the H3 norm blow up, because this is my choice what I choose in the cutoff argument. Again, I am saying that this is the choice, but what you can do, you can't improve it more, but you can consider W2 key instead W2 4, where key is less strictly than 6 in 3D. W2 key less strictly than infinity in 2D. Just small improvement, but it is like that. As I told you in the beginning, my alpha 1 is strictly positive. So here, what happens when alpha 1 is equal 0? You have better system. When alpha 1 equals 0, you have a lot of simplifications, taking into account this relation between the parameters. I'm not going to repeat arguments that I said in this second part in the beginning, but you see here that you don't have any more time derivative of Laplacian because alpha 1 equals 0. You have many linear terms disappear. If you have certain relation between the parameter alpha and beta, which is a bit restriction in comparison with the general setting, but this is because of the linearity. If you are in this setting where you have some epsilon 0 parameter satisfy this, you have global well-posedness of this problem in this sense. So it's typically in the same things. You have inequality satisfied under with some integrability information about your solutions and your formulations. What is interesting now is the beta term in comparison with the viscous term is more regular. It will give you more integrability of the gradient, which is important. From one side, it will give you the right, you can prove that your solution is just not weakly continuous with value in h, but in fact is continuous with value in h. It's continuous with value in h because you have more regularity in time. This is not correct in general for Navier-Stokes equation, at least in 3D. The other thing is having this information about integrability in of the norm of the gradient in L4 allow you to prove the uniqueness of the system even in 3D, which make this system 6 very interesting. So you can prove this stability result that I was saying, and therefore I have global well-posedness of my problem in 2D and also 3D. Once I have well-posedness, I can talk about the invariant measure now. So I have pathwise uniqueness. I will define family of operator. So in the following sense, given by 7. So if you give me an initial data y0 lives in h, and then I track the solution up to time t, then I take any bounded Borel functions on the Hilbert space h. I define the following map, which is well defined because I have existence and uniqueness. I prove, but by using by studying the miserability of my solution, that I have the following information about the conditional expectation given my filtration. As a consequences of this, I can say my my solution is Markovian, and therefore you see that the operator defined in 7 satisfies the semigroup property. So the fact is a semigroup on this space, in the space of polar bounded function in H. And keep in mind that the DL space of bounded Borel function on H is the space of probability measure. So this is what I am doing like that. Then I can prove the following theorem. I can prove the existence of an invariant measure of this semigroup in the following sense that I am writing here. So I have an invariant measures where this PT star is the adjoint semigroup of the semigroup that I defined in a moment. How I prove such theorem? I will use Krylov-Pogolydov method, which tell me that I can construct an invariant measure by doing some averaging technique. But here I am a more in stochastic framework. I will use this theorem in the frame of Feeler semigroups. What does mean Feeler semigroup? It means that my semigroup that I defined is a priori defined in the space of bounded Borel function in H. It tells me that it maps the space of continuous bounded function in H to itself. This is what tell you the proposition 1. I can use my stability result and some stopping time argument to prove it. Second proposition, since I'm using Bogridov-Krylov approach, I need to prove some tightness of some averaging measure. So if you consider the law of your solutions up to certain time t, given some initial data concentrated in y0, you can prove that the following property holds for the following ball, where the ball is the norm of V in R. And remember that V is something H1 is compactly impeded in L2. This tells me that the family of averaging is tight. So I can extract some sequences converge weakly in the space of measure. And this limit is invariant under my semigroup. This is what tell you Krylov-Bogridov theorem. And this is basically I use my a priori estimate. Once I prove the existence of invariant measure, I can go more to analyze my invariant measure. I can prove that my invariant measure is supported in the set W140, the Sobolev spaces. And from this information, how I can get this information, I just need to use my a priori estimate. And once I have this information, since X, which is W14, compactly impeded in the space L2, this tells me that the set of invariant measure, any invariant measure in this set, you see the set, it's tight. Since it's tight, you can prove that it has an extremal point. And then there is a characterization of ergodic invariant measures for Markov semigroup or general for semigroup that tell you that the ergodic invariant measures coincide with the set of extremal point thanks to Klein-Millman theorem. So thanks to the tightness property of my invariant measure that I prove, I can prove that I have an ergodic invariant measures. And by ergodic, I mean the following sense. I have certain relation between the averaging in time and the averaging in space. The advantage of this result that I can prove an invariant measure even in 3D spaces for this kind of model, which is something impossible for the 3D Navier-Stokes, for example. Thank you for your attention.